Thank you very much. So a pleasure being in Berlin. Yesterday was a little nicer than today, right? Today is a good day to be indoors and have meetings inside. So there we are. We're still inside. This is great. So pleasure being here. I'm going to talk a little bit about some of these emerging data-driven methods that we can start applying to physics and engineering problems. We all know that machine learning is playing a bigger and bigger role everywhere we go. We try to move this somewhere a little more discrete, maybe on top. And so part of the fluency now as any student in science and engineering or as a faculty is you have to have this new component of your research, which you have to be able to handle data. You have to be able to have learn about how to process that data and have access to deep learning algorithms. And this is made somewhat easy, right? By Torch and JAX. It's as easy as pip install Torch, right? Massive code base, access of things that you can do with this. And so how does that change what you would want to do scientifically? Because ultimately in science and engineering, the goal is to solve a problem. And you have one extra tool now available to you in 2023 that in 2013, you didn't have access to very easily. So just that decade alone has revolutionized what we can start thinking about. So the title of the talk, The Future of Governing Equations, I don't know the answer to it. So I'm going to tell you, here is the answer. But what I'm going to basically come to you with is some ideas about how we have to start thinking a little bit differently now that we have access to some of these tools. Okay. And the reason I kind of highlight governing equations is because most engineering design and practice is often framed around, I go pick up a textbook on fluid dynamics or optics or heat transfer. And out of that book, there's some governing equations. And mostly what we've done is we've done the forward problem. We simulate those governing equations with the idea that that will tell me a lot about the system. But now there's new things we can do with that, which is really revolving around data. Okay, so we're going to start here. And actually, it's not funny, right? So this is the Einstein-centered. But here is the quote that actually is completely relevant. It's from 1960 in one of his papers. And he wrote this because this is such a foundational concept when he was talking about relativity, which is the general laws of nature are to be expressed by equations which are both good for all system of coordinates. There's two words that I want focused on here: equations and coordinates. This is this idea that the physics side model, it shouldn't change whether I'm in a car moving by it or in a spaceship or rotating around when I measure it. It's the same physics, irrespective of the coordinate system. But how you represent the dynamics within a given coordinate system matters. And so part of what this talk is going to be about is all about this idea here. There's two fundamental things you have to think about when you go model a system. One is, which coordinate system am I going to use? And once you've made that choice, how do I express my dynamics in that coordinate system, right? And we've already had lots of examples across the engineering sciences where you've done change of coordinates, or, for instance, you even moved it to an eigenvector space, which is very nice because it diagonalizes things. These are all concepts that you're familiar with. But what machine learning is going to allow us to do is to do this at a much higher level than we've ever been able to do it before. Okay. So I'm going to give you a picture, because really this is what the talk is going to be all about. I'm going to take input data. Okay. Oh, things starting to I'm going to take input data into a neural network type architecture. So that's on the left. And this data can be collected from whatever device I have, right? So part of it is about sensors that you have access to. And that data is going to come into this pipeline through, I've already put this here, some kind of neural network architecture. I'm actually specifically thinking here of an autoencoder that drops it into a latent space. And in that latent space, I want to represent the dynamics. And I want to choose that latent space that is somehow advantageous. This is always what we do when we pick our coordinates and our dynamics. We're always going to what's the most advantageous way to express this? Because if I can do it well, I can understand my system and engineer the next system. That's why we do science mostly, is we understand something, we can build a new technology or take a next step to understand something further. We're ultimately interested here in extrapolation. I want to be very clear that this is not what most tech does. Natural language processing is not about extrapolation. It is about taking everything it's ever seen on the internet and interpolating. So what we're going to do scientifically is actually much harder. It's to move our models into a space I have no data. Okay, so just have that in mind, that that's going to be an end goal for us. And so let me bring this all together into an example that you are familiar with. And this is, for instance, planetary motion. And I want to convey this concept of learning coordinates and models together. So what you're looking at is the night sky. And in the foreground here, this is essentially the retrograde motion of Mars. Okay, that's the foreground planet. And over there is Saturn. And for millennia, what people wanted to figure out is, how does this work, right? What are the governing equations? Before we had lights, there's no light pollution. At night, you'd go up and you look at and it was startling sky, and you'd see this. And so there were 6 planets that we knew about, right? Until very late, even in the time of when we were in Copernicus and Kepler. And so people wanted to understand the motion of the planets. And so fascinating was this, that we gave them the name of like Greek, Roman gods. And so how do we characterize the motion? And the first successful theory came out of Alexandria, Egypt. Claudius Ptolemy came up with this mathematical description, completely geometry based. The center of the coordinate system is the Earth, and every planet could be represented about a circle, and then a circle on a circle on a circle, right? So you go around the big circle, and you're on another circle, and then in fact you could have even more circles than that. But even a 2-circle motion would be amazingly accurate in capturing this retrograde motion. Okay, so this became known later as the doctrine of the perfect circle. Exceptionally elegant theory. All you need to know is geometry. Remarkably, this is 150 AD. Euclid in 300 BC, so this is almost half a millennia before, wrote the book The Elements, which basically was a summary of all this geometry. Okay, and that book has been more reprinted and more sales, they estimate, than any other book in history besides the Bible. So there you go. That's important, because if you're thinking about writing a math textbook, you should think, okay, somebody could write something competitive with the Bible. So maybe it could be you. There we go. Okay, you got to be the elements here, though. So beautiful theory. In fact, this theory lasted like 1,500 years. Probably one of the longest lasting theories we'll ever see in existence. And in fact, this is sort of this beautiful picture of an Italian thoughts on the walls, where they have this painting of this coordinate system, this way of representing dynamics. Okay, so there was a commitment to a coordinate system, and then the dynamics on that coordinate system. One way to think about the circles on circles, it was the earliest version of a Fourier transform. Right, just represent things as frequencies. Pick out the right frequencies, put them together, boom, got this nice model. What would happen though is a coordinate change. And the coordinate change, here is sort of the major proponents of this coordinate change. We often think about Copernicus as the one advocating we should switch to the heliocentric coordinate system. And within that got picked up sort of really by Kepler and Galileo. And it was Kepler and Galileo who really cemented this coordinate transformation, especially Kepler. Kepler was the real mathematician here, who nailed everything down, constructed these elliptic orbits. He had Tycho Brahe's data. And the only reason he got it is because Tycho died. Right? Tycho was completely not open source. He wanted all the data. He didn't want to share it. The only way we got it shared is he died. And his family fought for him not to have the data. And with that data, it took him 11 years to get regressions to ellipses. Isn't that fascinating? You kind of wonder if he would have had a Jupyter notebook open. It's like, oh, you died. Here, let me just get a USB stick, get the data. Oh, ellipses, let's go have lunch. Right? I mean, with the power of scikit-learn now, it's pretty amazing what you could do. But really, that was that was the heartbeat of that transformation of understanding the motion, retrograde motion, not as circles on circles, but as, oh, they're both on circles. And the reason you see them differently is because they're moving at different rates. Okay. So this is a new coordinate transformation. And by the way, I want to also mention the following. A lot of people believe Copernicus was one advocating this idea. He was not. This was also advocated around the time of Euclid by Aristarchus of Samos, who studied at Alexandria too at the same time. Euclid was also at Alexandria. Alexandria is the most fascinating city, in my view, of the ancient world. It's an amazing city. And he had this idea at like 300 BC. The only reason we know about it, because everything he wrote about it was lost, is that Archimedes wrote about it. Archimedes said, this is like the dumbest idea ever. Okay, he didn't say it that way, but he was very scathing of the idea. So that was my paraphrase of what Archimedes said. And it was Copernicus who said, is that true? Is that the dumbest idea ever? Well, maybe it's not a dumb idea. Maybe we could do this representation, okay? And once you make this coordinate transformation, 87 years later, Newton comes along and you have F equals ma. If you're going to get F equals ma, you first need the right coordinate system. And so we had the coordinate system after 1,500 years, 87 years later. We have F equals ma, and we think we've got this thing figured out, except for 227 years later, with increasing evidence, the data that we collected, we got better and better measurements of the planets. It's like, it doesn't seem quite to fit F equals ma. That's what led Einstein to posit the theory of general relativity. In fact, it wasn't quite F equals ma. Massive bodies distort space-time, a new theory. And you only got to this theory because you finally had good enough measurements. I think an exciting time right now for you guys. I mean, by you guys, anybody under 30. We just, that new telescope just went up, right? This is amazing that the quality data it's going to get, it's going to probably give us a picture to the right of Einstein at some point. At some point, well, Einstein was mostly right, but really here's how gravity works. Always when you have better data, you're going to have a better model. So let's review this because it's really important about representation. Model 1. The idea is I take the data, I come through this autoencoder, I learn latent representation. My latent representation being Ptolemaic model. Circles on circles, come back out. Perfectly valid model. And in fact, it's just as accurate as F equals ma. There's a huge advantages to this model. I don't have to know any calculus. I don't have to remember differentiation rules. All I have to do is draw circles. Okay. Model 2. Alternative. I come through that autoencoder. I learn a latent representation, which is our typical picture of the solar system. And then in that, I learn my dynamic model is F equals ma. Okay. They are equivalent. And this is exactly what Einstein is talking about. Here are two models representing the same phenomena. And you can do different mathematical architectures to get at them. Okay. But here's the thing I want to highlight. And this is also an important piece of this talk, which is the acceleration of science piece, which is you think about all this architecture being in play to develop these models. And we had geometry as far as 300 BC. It's not like Euclid came up with it. Euclid synthesized it all into this one book. It's 300 BC. It still took almost half a millennia just to do circles on circles. This is not like some massive leap of intelligence. This is okay, circle and circle, right? You're just using the very basic building blocks that have been around for half a millennia. But that was the first successful theory for the motion of the planets. You skip 1,500 years to decide to make a coordinate transformation. Okay. And by the way, that coordinate transformation wasn't easy to make. Mathematically, it wasn't so bad. Philosophically, it was really tough on some people, right? Galileo was under house arrest for the rest of his life. He was forced to recant all of it, and he did. He was a pretty bitter man, I think, when he died, right? Because he was right. But he was forced to recant it all and so forth. By the way, the example that was before him was that just 6 years previously, Giordano Bruno was burned at the stake for not recanting those ideas of a heliocentric coordinate system. He also had some very other interesting ideas. And so Galileo decided to take the safe path there. But like that came at great cost. It should have never come to that. 87 years later, you have Newton, general relativity, another 227 years. So we see this massive scale of innovations in theory, right? And so part of what machine learning can do, and what we're hoping this will do for us, is accelerate this, right? All this kind of things that we do, looking for coordinates, looking for models, we can now put it in Torch or JAX and say, here's my data set for this material that I don't know how it's behaving. Am I going to wait 1,000 years to learn how it works? Or can I take enough data and like let this thing just crush through this and try to find models for me as a helper? Okay. All right. There's also a big difference here, and it's really important, between these two, Kepler and Newton. What Kepler did is wrote down these elliptic equations, right? And Kepler's laws. And what he did is he fit that data, right? His models fit the data that he had. F equals ma. Why is Newton more famous in some sense, right? Newton is more famous because he has F equals ma. But if you solve F equals ma, what do you get? Kepler's solutions. But why is Newton more famous then? Because what Newton did is he now has a generative model. He has this thing F equals ma. And then you can start saying, I wonder about the following. What would it take to launch a rocket from the surface of the Earth, put it around the moon, circle a bunch of times, and bring it back with somebody on board? Oh yeah, and by the way, drop someone on the moon, bring it back up, come back. Kepler can't even conceive of that question. Kepler is a fit to the data. This is a massive extrapolation. I've never seen it. I've never ever. Okay. The best you've seen is someone threw a rock in the air, right? Okay. So this is what we want to do as scientists, is this. Like, imagine the following. Could I do something like that with my physics? Now, how much did we trust F equals ma? Well, when we first started launching rockets, they had nobody in there. And then they had like a mouse and then a monkey. Because we had to make sure the physics was the same up there, right? And then you finally launch a human, and then you do this whole thing, right? So you build the trust in the physics. So I would say the left represents what you might call ChatGPT. ChatGPT isn't smart. ChatGPT is an interpolation. It's seen the entire body of all of GitHub. It's seen the entire body of all of literature. It's seen so much more than you've ever seen. So you're amazed by it, right? But the fact is, it's an interpolation engine. What NLP is. Okay. All right, so let's talk about where these two ideas come to play. They come to play in modern architectures like robotics and cars, self-driving cars. These are both autonomous agents, and they are sort of, in some sense, the dream of where machine learning might be going one day. We still don't have self-driving cars really on the road, right? By 2020, they're supposed to be taking over everything, but do you see any? I haven't seen any, right? I don't think, there are any in Berlin? I don't think so. Why is that? Maybe we come to that, because if you're going to put that on the road, you better know how to extrapolate. What happens if I've never seen this thing? Should I run it over? Right? So it becomes something you have to be really worried about. The robot, and by the way, the philosophy of these two is quite different. That robot is built with physics-based models, because one of the difficulties of that robot is that it has to, even standing up is a physics-based act. right? You got to have balance, right? And so this is physics imbued, whereas the car is just sensor imbued. Just train everything on massive data sets. Okay, but even with all the training we've done so far in self-driving cars, you can't, it's an interpolation engine. Okay, and so I just want to highlight that because essentially these two technologies pick up the legacy of Newton and the legacy of Kepler. No physics, it's an interpolation engine, and that's physics-based, roughly speaking, right? Of course, they've put some physics modules types in cars, you know, and it made it more advanced, but for the most part, it's based upon just rules. All right, and by the way, even if you start doing machine learning on some of this and using all your best data-driven skills, and you know, these things like this slipped, right? You see all these very human-like failures. Here you go, Friday night in Berlin. Oh, okay, that was too much time at the Christmas market. Oh, yeah, okay. Maybe not on Monday, but certainly on a Friday. Hopefully you guys are having fun out there. Okay, so these failure modes are basically trying to teach a robot how to do things robustly, and you mostly get it right, but like, I don't know if anybody's had a broken arm or broken, this is probably what happens. Something like this happens. I've had broken foot, broken shoulder, broken, I've had all kinds of accidents. So I'm just like this. And so even if you have good algorithms, you know, when you get to engineering, control and design, it's still pretty tricky stuff to do. All right, so let's get to what we want to do here specifically in building up methods. This is the mathematical architecture. It looks fairly simple in many ways, right? What we have here are measurements. So that's what the YFK stands for. YFK are our measurements, and we collect them at different time points. And the measurements are going to come from sensors. And the sensors could be something like this. I film an activity. I put cameras on my device or on my physics-based device. And I want to say that's my sensor monitoring the situation. Or I film physics. This is the cheapest and best sensor we have. Dirt cheap. Here's the second best sensor we have, a laser. Okay. And so these are really cheap technologies for measurement and monitoring. And neither of them know what the governing coordinate system is. It's just bringing in pixel space or light coming back, and then you need to interpret that. So what this is going to take measurements in time. And what I'm going to try to do is three things. So first of all, I give you one measurement, you're giving me three things. That means I've given you an ill-posed problem. You're not going to be able to do what I'm going to ask you to do, but let's just walk through what I want you to do. The first thing I want you to do is learn from the measurements how to go from the measurement to a coordinate system. So you have to discover a measurement model. Oh, you're measuring pixel space. Oh, from the pixel space, there's this object in there. I'll pull out the object for you. That's H. Once I have that, I've got to determine what is the actual state space representation of the dynamics, X. What's the right variable to be using? And then what's the dynamics, which would be prescribed by F. So if we look at that night sky picture, I give you a video of the night sky. H is telling me, oh, there's these objects in there, what we call planets. X is telling me about the position and its velocity, because I need those two. And F is then the F equals ma physics that I would get from it. So that's the idea. Is from a video, I need to pull all that out. This is terribly ill-posed. Okay. And so what you've got to do if you're going to make it a well-posed mathematical problem is you take ill-posed problems, and all you got to do with ill-posed problems is add regularizations or constraints. And then it's going to be well-posed. So what kind of constraints and regularizations we're going to add? We're going to add things around interpretability, parsimony. In other words, we have a rich history of building physics-based models, right? We built this entire iPhone, right, which everybody has as their life partner. Maybe not an iPhone, but a smartphone. That's your life partner. You might go through boyfriends and girlfriends, but okay, you might dump this phone for another one, but really you just upload what was in the other one to this one. So it's really your life partner that you can't go anywhere without. You might go on a subway somewhere and like, I don't know where my buddy was somewhere. I lost him, but you did not lose your phone. You never lose this. This is your life part. And we engineered this through extrapolation. We had quantum mechanics, we had electrodynamics, E&M, and over time, we figured out how to build one of these things from those technologies. That's exactly what we want to do here is we have models that we could understand, which allowed us to extrapolate, which allowed us to extrapolate, which allowed us to extrapolate, and then we end up with something like this. And so we want to go with this idea of being able to have models we understand so we can extrapolate. So this goes back to the interpretability piece. And these ideas are old. They go back to like William of Ockham, 1200s. This is right when it was okay again to start thinking about logic, and Aristotelian logic was not just outright a bad thing to be doing. And so in Oxford, they started building logic again and started constructing Aristotelian logic. And William of Ockham was very much an advocate of the simplest explanation is the best one, essentially. Don't build this giant constructs of logic that are meaningless. You should have the nominal representation. And so that was sort of the advocation formally first, then from the 1200s. And of course, you see it throughout history. I put Pareto up here because Pareto also, we talk about Pareto optimal, Pareto front. These are things that come up in model selection literature. If you come, especially from the biology side, you'll hear Pareto's name quite a bit. And so what we're actually aiming for then is two things. We're going to think about these are sort of parsimony interpretability. It's the ultimate in physics regularization, where we want the smallest number of terms in the smallest number of dimensions to represent what we observe. Okay, that's going to be our sort of what we're after in all this. Okay, so, but even if I say that to you, there's still this issue that I just showed you right slide 2, which was Einstein said, well, there's kinds of coordinates and equations, right? They're all going to be equivalent. So how are we going to do this? So I'm going to give you one last example, then we'll move right into different selections of methods. So let's give you what's called the Berger's equation. This is some partial differential equation. We'll call this the truth, right? So this was derived in the 40s when we were trying to understand shock waves. We hadn't created a shock wave yet in terms of, this was for supersonic flight. We were trying to see what happens if you break the sound barrier. Will we all die? Nobody had gone through the sound barrier, right? And the plane hadn't gone through it. So they were like, weren't sure a plane could do that. And so they started understanding what is a shock? How does a shock behave? So let's call this the truth. And so people were very interested in studying this as a simple model, the simplest model of shock creation. And in 1950, independently, Cole and Hoff found this transformation. If you just changed from the original coordinate U to V, and it's a nonlinear transformation, in this new coordinate system, it's linear. That's the one thing you know how to solve analytically, is linear PDEs, linear equations. And so they said, oh, great. I have a new variable that I could actually trade to, where now the dynamics is very simple to represent. But once you have that, you say, well, but that doesn't really matter. What really matters is the solution of that equation, which you can write down. It might look something like this if you do a Fourier mode expansion of this thing, and maybe you do a finite version of it. Oh.
是吧？不可能卡的，用那个键。
Kids on. It's awesome. And by the way, this is the dynamics of this. So in other words, part of what I want to show here, these are all the same representation of this. I could write it as that PD, that solution, or give you a picture, give you the actual data. They're all equivalent. This is exactly what Einstein's talking about. So the question is, or I can do a discretization of this. So what should I learn? Einstein says there's all kinds of representations. So now it's up to you to decide what to learn. And by the way, I say it's up to you because it's not up to me. When you have your code, it's your code you're in charge of. No, I'm not in charge of your code. Who's the boss of your code? Oh, you guys don't know. Okay, so like when I ask who's the boss of your code, you should say, I am. It's on your laptop, right? So you get to decide what comes next. Okay? I hope that's empowering and not frightening. All right. So we're going to go right to here, Einstein. And by the way, you don't have to worry about if I pick something wrong. What Einstein says, there's just different representations. Doesn't mean you couldn't be wrong, but I'm saying that if you pick one thing versus another, if you get the representation right, it's all good. All right, so let's talk about what we want to do here. So here's the dynamics, here's the measurements. Since I have choices, now it's my choice because I'm up here giving the talk, right? See that up there, the dynamics, I could pick nonlinear dynamics. What if I just say, well, what if I picked a coordinate pairing to go with the dynamics where I want F to be linear? I just showed you that Berger's equation and that there was that Kohlhoff transform that allowed me to build a linear model. So maybe there's a coordinate system with all these dynamics I measure where everything's linear. Now, the reason I want to do a linear model is because I know how to solve those. It's the only thing I really know how to solve, right, analytically. And so, I mean, I can solve nonlinear things, put them on a computer, but I want a linear model because I just write down the solution. By the way, and are there limits to this? And part of the limits to this, I do want to highlight one thing, which is you can only discover models that are not sitting below a noise floor, right? If I take a measurement and here's my noise floor, I can't discover physics way down here below the noise floor. We can't even see it. It's indistinguishable from the noise. It's buried under the noise. So just have this in mind. One of the things that we studied was exactly this in terms of learning what is the possibility of what you can learn. And this is why we didn't know about general relativity until Newton came along. Einstein came along, because we didn't even have the data to see it until the late 1800s and early 1900s. Right? We couldn't even tell it was there. Right? That's what's going to be amazing about this new telescope. It's getting us an order of magnitude better measurements, which means we're going to see stuff that's like, that doesn't make sense with that theory. I'm sure of it. And then we're going to have to come up with a new theory to explain it. So let's talk about linear models, because they're the simplest to work out. And the easiest thing to do with data in general is to do what's called the dynamic mode decomposition. I don't know if you guys have heard of this method, but all you do is say, okay, I'm going to just take this data and fit it to a linear model, which is x dot equals ax. Okay. And so here's my data. It comes in a stack of, I measure it in different time points. Okay. And what we're going to do is going to take this, and what I'm showing for you here is sort of in some sense the state of the art of the DMD method, which is first it was developed in 2010. The algorithms developed up until very recently give you, especially if you have noisy measurements, give you terrible models. Let's be honest, right? Because I've actually worked on this for a long time. So you'll read a bunch of my papers that are bad methods. Okay, so I'm cutting myself down. So you know that I'm not probably lying if I'm sitting here saying, don't read my, but after 2018, and if you read my papers, it's probably okay. Okay, but before that, you read those papers, you say, oh, he's probably lying. Now it's okay if you think that. Okay, so DMD basically takes snapshots of the system. There they are. And what it's going to build for us is a linear model. And here is the linear model. It's an exponential solution. It's basically, if you have x dot equals ax, you just put an exponential solution, e lambda t, and the solution, and then you do an eigen decomposition. And so you get the eigenvalues, eigenvectors, and the eigenvalues are the time dependence, the eigenvectors are the modes, and then each one has a loading, how strong it is. And that's exactly what this is here. And what we do with this is this optimized DMD algorithm, which is a direct bit to these exponentials. And we do statistical bagging. That's what Dia Sadashar did, where you take different snapshots, you build a whole ensemble of models so that you can get the best one. So it really works well with noisy measurements. Okay. And by the way, if you want access to this, you just do pip install PyDMD. Boom. The latest version of PyDMD has these methods built in, partly because the previous version of PyDMD, if you tried it on real data with noise, it's not going to work. Unless you had perfect data, it doesn't work very well. Okay. All right. The other possibility, so that's just a straight regression. It always works in terms of giving you a linear model. So that's partly why people like DMD. It's just like, that's like the first thing you should try. I have data. I want to build a dynamic model. First thing you should ever try is try bagging bot DMD, bagging optimized DMD. Just see what it gives you. And by the way, that's the baseline of what you should, if I'm going to build a fancy model, you have to beat bot DMD. Okay. If you build I'm going to build a neural net that does this, and you can't build bot DMD, you just wasted all your time. Okay. So have that in mind. It's like it's the baseline you're trying to actually beat. So here's what Bethany did to try to beat something like this. We're not going to go right to that neural network architecture, which say, all right, I took a measurement. What I'm going to do now is I'm going to have a neural net, and that neural net is going to have one job: learn a coordinate transformation for me. Okay, that's what it's going to try to do. Learn a coordinate transformation for what? Try to find me a new coordinate system, a latent representation where the dynamics really behaves linearly. Now, this is what neural nets shine at. You're pretty explicit about what you want. It's going to give you the best shot at getting there. So here, what we're looking at is learning a coordinate transformation to a latent space. And in that latent space, when I go from one time point to the next, it's going to be a linear map. Go learn for me a coordinate pairing. You see what I'm doing? I said with Einstein, you have to learn coordinates and dynamics. And what I'm saying is, I want my dynamics to be linear. And the pressure on that neural net is to find you a coordinate system for that to be true. And I'll try to do the best job possible. In fact, this works quite well. You take something like this, flow around the cylinder, there's a picture of the dynamics of this thing. So, it's von Neumann vortex shedding off the back end of this thing. So you get these nice nonlinear structures. You can collapse it all down to a low rank representation. You say, I want to turn this into a linear model. And that neural network do that. So this nonlinear dynamics is now in a new coordinate system where that behavior is purely linear. Okay, under that representation. So these are the kind of things you can start to do with neural nets that you can't do with your analytics. We did harder problems. This is with Craig Jin, where you take something like the Kuromoto-Shibashinsky equation. So if you don't know what that equation is, it's a partial differential equation. It exhibits spatial temporal chaos, and people love it because it's hard. Right? It's a paradigm for hard problems. And then you can still just simulate it easily on your computer. But, understanding its basic dynamics has been something that the community has considered for quite a long time. It's a very rich problem. So one of the questions that Craig asked is, well, could I find a coordinate transformation to take this system that generates spatial temporal chaos and make it linear? He actually did. He found an embedding, a coordinate system where the dynamics is approximately linear, which this result has surprised so many people, including myself. Because this is the kind of problem, like, there's no way you could find that. Maybe we can do burgers because we knew that, somebody had done it. This tells us something very rich is happening here, that the neural network can do it. It can actually find, to use this coordinate system, this thing looks linear to me, largely. This is what the network says. This is what the full PDE says. And they match up beautifully across so many different simulations. Okay. And so there's something here to be learned, which is a couple of things. First, I think this result highlights that there is something for us still to learn on the analytics side, which is if you can do this for such hard PDEs that it can do this, that means that maybe we could do this actually in practice with our analytics. That's what it tells me. Just we haven't been smart enough to do it. Okay. But that's kind of where this thing goes. And so that's kind of where we've taken it. You can also learn Green's functions. I don't even know if people learn Green's functions anymore in engineering. But Green's functions are these fundamental solutions for linear problems. And basically around the 90s, we stopped kind of doing much of it. Why? Because around the 90s, early 90s, everybody started getting access to these things. Right? Computers. And so I can just simulate nonlinear problems without a problem. When I was in grad school, the one computer that was there sat in the lab. So you had to go into the lab, program it on, right? The internet hadn't been invented yet, right? Nobody had laptops. So you had to go to the lab. So it was just starting to happen right in that early 90s that generic grad students started having access to computers. But by the mid 90s, now we had access to laptops, and then everybody can solve these nonlinear problems on their computer. And then we ditched Green's functions. But what this does, it says, well, actually, maybe we don't ditch the Green's function. We just learn a coordinate transformation to make it, again, mostly linear. And in that linear space, now we can use your Green's functions and find fundamental solutions. So you can find Green's functions for nonlinear problems. Okay, notice what I'm doing here. What I'm actually doing is I'm taking my space and warping it to create a new latent representation where everything becomes linear. Okay, it's a little bit of my path of the opposite, of an object looks all, curvy. You can imagine there's a coordinate system in which I straighten that out. This is exactly what I'm doing. Okay, I'm not doing anything fancy but that. I've been doing it with the spatial domain, but I can just as easily do this in the time domain. And so I can warp my time coordinates as well. And this is what Henning Lange did. He said, well, okay, so don't warp your space, warp your time. So for instance, here's a signal that you're looking at here, which is quite spiky, right? So it like has big spikes. And if you were to use Fourier modes here or linear model, which are going to be exponentials and complex and exponentials of Fourier modes, you need a ton of Fourier modes to resolve spikes. But it looks like a pretty simple signal, really. But not from the Fourier point of view anymore. So you could represent it as Fourier mode, or there's this idea of Koopman embedding, which is to say, change your coordinate system, warp time. And the way you do this is you say, right here, see this S of theta? That's going to be a neural net. It's going to take my time series, find a way to warp it so it looks as if it's sinusoids or linear. So you warp time in order to represent this. And so this works amazingly well in terms of doing prediction. So we did something like we forecasted power grid data, which has some chaotic spatial temporal behavior. And it's quasi-periodic. And we just did forecasts on this. And this, by warping this, you can see the performance of this in terms of doing true forecasts for long term and short term. And this Koopman forecasting method, the only reason I put this up here is there's a common phrase in the machine learning literature, oh, like LSTMs will beat everything. I just want to show you this. LSTMs, gated recurrent units, echo state networks, these are all your modern machine learning tools. They all lose to your smarter physics-based modeling paradigm and sticking with it and just using the neural network to help you do a little bit better with your interpretability. So if someone just says, no, an LSTM will beat you, I always love this slide. I feel like it's like, well, yeah, I don't think so. This shows me that if I'm smarter about what I'm doing here, I can beat some of these neural networks that have no physics built in whatsoever. Okay. All right, and here's things you can do. Here's a model reduction technique. You take this full PD simulation of cavity-driven flow, you reduce it down to a low-dimensional subspace, you warp time, and now you have a model that you can simulate, which is this thing here. And this thing here is not even a simulation. You just have, here's the representation. So if I want to know what the solution is at time 1 billion, I just put t equals 1 billion in there, where I have to actually run that thing out to t equals 1 billion to actually get an approximation to the solution. So that's the power of these representations. Once you warp this, you have an amazing way to represent solutions for ourselves. All right, so those are linear models. And in some sense, I always say, well, a good start point, if you have real data and you're trying to build models, you start off with DMD. That's a really simple go-to. Bop DMD, just say, what does this give me? You can see you can still build more interesting architectures around linear models, but we can also go to nonlinear models. And there's a reason we might want to go to nonlinear models. Linear models have this underlying failing, which is first, if you have parametric variability in your data, a linear model works in one parameter regime. And it can't handle bifurcations, in other words, change in transitions in the dynamics. Linear models can't accommodate that, unless you build one linear model here, one linear model there, one linear model there. Nonlinear models can sweep through these things. So we come back to this. And we want to do this, but now you see this F, the F here, I want that to be nonlinear dynamics. Okay, so I'm not going to say be linear. I'm going to say, give me a model, but I'm going to restrain it. I'm going to say, give me something that's parsimonious. In other words, you get to use nonlinearity, but you can only have 2, 3, 4 terms there, max. If you have more, I penalize you really hard. Why does that even work? It works partly exactly why we have governing equations. It works because of what's called dominant balance physics. If I were to take this, and everybody at home, don't worry, I'm not going to hurt anybody with it. It's a remote control. And if I were to huck it, just throw it over to you guys over there. And I'd say, please model this for me. I say, oh, that's like F equals ma physics, right? There would be some trajectory. And then I would ask you, well, why didn't you include thermodynamic effects? Why didn't you include the quantum fluctuations that were there? Why didn't you include the electromagnetic energy that's hitting it and reflecting off? What would be your answer to that? Does E and M not hold when I throw this? Does quantum not hold when I throw this? The reason those things don't hold, they're like, well, it's so small compared to the big effect, which is gravity. That's exactly why when we model complex systems, there's always more terms, but what you see is the manifestation of the most dominant terms there. And typically, and we've shown this over and over again through all fields, that's like 2 or 3 terms. Navier-Stokes, fluid flow, it's like 3 terms there. Does fluids not have quantum mechanics in it? Does fluids not have thermodynamic effects too? Of course, it has all those. It's just that when we typically visualize fluid flow, the dominant effects are sitting there with that name terms that we have. Does that make sense? Hopefully. So that's what we're going for here. We believe when we measure a system, what we're going to see is the manifestation of the dominant effects. And that's what we're going to go after. So how are we going to get it? We're going to use what's called sparse identification of nonlinear dynamics, or SINDy. And what this is going to do, it's a very simple architecture mathematically. It's AX equal to B. So let's talk about what A and X and B are. A is going to be a matrix of potential right-hand side terms. So remember, we're trying to model X dot equals F of X. So X dot, if I give you data, time series data X, you can produce X dot. You differentiate the data in time. So there's X dot. That's going to be B. But X dot equals F of X, and you don't know what F of X is. Well, I don't know what F of X is, but F of X is going to come from a candidate set of terms. That's what the matrix A is. Here's all these candidate terms that might be part of the right-hand side. Now, how do we come up with candidates? Well, we've had centuries and centuries of experience modeling physical systems. So you just say, well, here's all these types of systems I've modeled, put all those terms into my potential candidates of terms that might be in the right-hand side. So that's A, that's B, what's X? X is telling me, out of these candidate terms, it's telling me the coefficient in front of each candidate term. Now, here's where my giant bias comes in. What did I say I wanted? I wanted a model with as few terms as possible that has dominant balance physics. So when I solve this AX equal to B, I want almost everything in it to be 0, as many zeros as possible. What does that mean? It means of all these libraries, only these 2 candidates matter. Maybe I had 100 other candidates. No, few as possible. So I do sparse regression, pull out as few candidates of library terms as possible to model my system. So if I come in with the Lorenz, I give you data X and Y and Z time series data. You know what it came from? You can certainly produce X dot, Y dot, Z dot. You can certainly regress to candidate libraries. And then what happens when you do the sparse regression, dots tell you the non-zero terms left over. And what do you get out? You get exactly back the Lorenz system. That was actually what produced that data. So this kind of architecture, we've done it for spatial temporal data as well. So I just give you data, right? Here's the data. I give you XT, right? I say, what produced this? What produced this? What produced this? You regress into a library of potential terms. And here's, for instance, these different models we pull out of those data sets. KDV and NLS, reaction diffusion systems, Kurman-Shevchinsky, Navier-Stokes. Okay, so what it's discovering for you is the governing equation that's responsible for producing that data. And that's actually part of the philosophy we're going for here, right? The philosophy we're going for here is whatever I'm measuring, there's some underlying governing type of equation, some governing process there. And that's what I'm after. So from that data, how do we get back to extracting that out of that system? I will say this, I'm going to present another package here. pip install SINDy, boom, you have access to all of it. And this new version 2.0 is really great. Ton of examples to work through. So if you want to do this with your system, there's a really great, well-developed mathematical computational framework for you to start playing with. Okay. All right. So how do we use this in combo though, with the fact that if you notice, one of the things I swept under the rug here, I assumed I already knew the coordinate system I had to be in. Like I gave you the state space variable, find the governing equations. More generally, you're going to say, here's some data. I don't even know what the right coordinates are. And this is Kathleen's work. And I'm going to show you an example of this in practice and finish the talk. So what Kathleen did is she said, okay, the fact is, if you measure a system, if you already know the physics, I mean, come on, then you're just validating what you did. But if you go to a real system where you think, I don't know what physics is, I don't even know what the coordinates are, how do you get this working together? So here's her paradigm. You see, at the beginning of the talk, we gave you this picture, and this is where it comes from. You're going to come in with data, maybe a video, and you're going to learn representation into a latent space. And what do you want to happen in that latent space? I want to do SINDy in that latent space. And I want a good SINDy model. In other words, some governing equations with a few terms. Okay. Here's the entire loss function. Not even that big. This is programmed, by the way, in TensorFlow 1. Right after we put this up, TensorFlow 2 came out. Right now, TensorFlow's out. So now we have Torch or JAX. I think we have a Torch version now of this. Okay. But philosophically, this is a major leap for us. Here's why. Take the simplest model you can. And by the way, this simple model, what I'm going to show you is a really hard problem. This seems super easy, but in practice, this is, I would say, state of the art in terms of models discovered from data. I give you a video. Okay, these are 2 example videos. So I just give you this video. So what you get at the input is pixel space. Okay. Now your computer has no idea what the relationship between pixel space and this pendulum is, right? Now you are biased because you already know what a pendulum is. So you're like, okay, that's just a simple pendulum, right? So in other words, you've already done a coordinate transformation in your head. You already know how to represent this. Theta, theta dot, theta double dot. You know the governing equations of a pendulum. Computer knows nothing. It just has pixels lighting up. So the pressure here on this neural network is to learn the coordinate corresponding to a governing equation. In fact, when you pinch this down and say, you must learn from me a parsimonious representation, it forces this neural network to say, the only way I can do that is if I get this variable right, theta. It gives you back theta, theta dot, and then in that, it will give you back this model. Okay? That's the simplest example we have. This is very hard because the only other thing I'll point out to you is, see the shadows? The shadows make it very hard. It's not just learning how the pendulum swings. It's like, it's also looking at, oh, wait a minute, there's a lighting model. Isn't there a light over here? Because it's showing shadow here. Like, so it's very difficult for it to actually do in practice. And we didn't realize this for quite a long time. Like, why is this one so hard? It's just this stupid pendulum. And everybody thinks this. Like, how hard can a pendulum be? It can be really hard. Because when you measure things, you get lighting, you get all these other things that are there that you totally dismiss with your eyes. Okay? Not just you, I blamed you. I dismissed with my eyes, so I'll blame myself. How's that? Okay? All right. So let me show this paradigm and we'll finish this up. And by the way, we've really stabilized this. There's Urban Fazell. He's one of the people I'm visiting in Imperial who does ensemble SINDy models, which is how do you make this robust under noise? Mars Gao, who did this even more robust to noise by doing a Bayesian version of this. This is super awesome. This one here can actually do raw video, what Mars has done. This is the first time we've been able to say, I don't even pre-process the video. Mars can just go straight from video to get the right model. Okay, but I want to highlight this. Let's go to a system, because they are the pendulum, you think it's too easy, right? And this is what reviewers say, the pendulum seems so easy. Why don't you do like 3 or 4 other models? It's like, nobody can do the pendulum. We could just barely got the pendulum to work, right? Because we're moving this along. So here's one though, that's very interesting. And this is with Ryan Rao And I'll finish my talk with this one example. You notice the architecture I'm going for here, encoder, decoder, latent space. What is I'm measuring? A mouse. And what happens with this mouse is they're going to take a bunch of measurements of this mouse while it's on a running wheel. What it's got is a little port to view its brain activity. So it's going to monitor blood levels, calcium imaging, neuron activity. It's going to also monitor on this little helmet. It watches pupil dilation, whisker fluctuations. Okay, all while this mouse is being shown a movie. Okay, so pretty diverse measurements. Here's what, for instance, here's what's happening with the eye observations. And what we're going to do is make a fundamental conjecture and say, underneath all this stuff that's happening with this mouse, there's some dynamical system in there. We don't know what it is. Is there? Could we find one or evidence of it? So what we're going to do is kind of try to think about building a model where we take the eye fluctuations, those are on the left, stack them up, run them through an autoencoder. And by the way, this is a time delay embedding. What time delay embedding does is it allows you to enrich the observer space, okay, and pick out the latent space. We're going to run it through the encoder into a latent space. And now we're not going to decode back to it. We're going to try to decode over to brain activity. In other words, if I just look at your eye pupil fluctuations, could I tell you what's happening globally on your brain? That seems rather miraculous. But here we go, 99-second video. Left, that's the brain of the mouse. Right, this is your reconstruction of what's going on in the brain from viewing the pupil dilations. So the pupil dilations or easy access are telling you brain-wide global activity, right? And this is like the video that kind of really shows this kind of architecture. It's quite remarkable, right? I mean, this is biology, right? So the hardest thing to work on is biological data, in my view, because it's crappy, got a ton of noise, and we don't have F equals ma anywhere, right? For the most part, it's like free for all. Right? We don't have conservation of mass. Is there a conservation mass in the brain? Is there conservation? We don't know. Right? We can't derive these things. And so we have not even a baseline rule set to go after, right? Where physics-based systems you do. So here's what we really did then, is we said, okay, take the eye movement, and can we find this common encoding? Here it is. From the eye, just looking at eye dilation, you can actually reconstruct then the calcium activity on the whole brain, the metabolism on the whole brain, hemoglobin on the whole brain, all from just looking at the dilation of the eyes, right? And this is what that common shared space looks like. It's massively low rank. Like, this is a real picture of this thing. And it looks like a heart. So what we're trying to do next is discover physics here. The problem with biology, though, is why haven't we done it then? You could ask, well, what's the governing equations of this? Well, part of the problem is that when it's biology, there's all these stimulus going on, which is like a control signal, right? And if you can't disambiguate what's the control signal from the dynamics, it's really hard to do. But everybody suggests that there is a low rank subspace. Let me give you this context in terms of biology, in terms of physics-based model. Remember the pendulum I showed you? Now imagine I put a bright light on it, I turn off all the lights. All you see in the pendulum is light, but then I went behind the pendulum and start kicking it. But I didn't tell you I was kicking it. So I'd say, discover physics for me. And then all of a sudden the pendulum's going like this, and all of a sudden it just does weirdest things because you didn't know I was standing there kicking it. That's like biology. We don't know what's kicking it. Like you're showing different movies. Maybe it tripped. Oh, there's a weird rough spot on the ball. Maybe it's thinking about, going to the pub later. Mine's probably don't think that, but you certainly do, right? Okay. Or a Christmas market. Maybe you're thinking, oh, what am I going to pick up at the Christmas market tonight? Whatever you're thinking about, it's all sitting in your brain, maybe affecting this. And unless you can tell where the control signals come from, you don't know what the real underlying physics is. And so this is kind of like where we are currently with all this kind of architecture is ending in these kind of places here And I'll just stop here because I think this is starting to highlight a little bit of this concept, right? Which is the one thing I wanted to advocate for you is that two things are your responsibility. Finding a good coordinate system, finding dynamics there. And I've shown you different kind of architectures that allow you to get some really interesting representations of dynamics and coordinates. And then, of course, for you, let's say as an expert in your own field, right? So you were talking about photovoltaics, right? Maybe there's something there that you say, I have expertise, I've studied this for a while. I can make more sense of this data and it will help you advance in your understanding or whatever you guys do. So with that, I'll stop and we'll go from here. Thanks.